because I'm sure, as you know, lab math is super exciting. Um, Everybody took general chemistry, right? How much did you hate it? Who hated it? Like, seriously hated it. Oh, okay. Only a couple people. That's impressive. Okay. Well, that sucks for you because you can check out of Chem 105, but you can never leave. You are stuck with it for the rest of your life so long as you stay tangentially within the sciences or related to the sciences, mathematics, medical school. It's all in there. So unfortunately, it is a necessary evil, but there's a lot of tips and tricks you can use to help it make it more bearable. I'm a PhD student in environmental chemistry, and I've tutored this for 4 years, so I get very excited about lab math, and hopefully you guys will get excited too. So a couple of goals: to be able to understand concepts such as dimensional analysis, molarity, preparing solutions, and just general problem solving is most of the time is it's getting in that right mindset of solving those problems and how to approach them. And if you can do one, you can do them all. And then at the end of this, as was said, there will be a little lab activity to see how well these concepts permeated. So this is you guys right now, face down, crying. Why lab math? Why are we doing this? Well, there's some major consequences if you don't have your lab math correct. For example, the NASA's Mars orbiter, that was a $125 million error. Half the team was using metric units, half the team was using imperial or American units, and the whole thing just totally missed, crashed, destroyed, gone. So that's a pretty expensive mistake, and you don't want to be that guy behind a mistake that catastrophic when it could have been prevented by just double checking the math. Another example of that, this is a recent article that came out in CNN, which is the periodical that's produced by the American Chemical Society, is this paper about fracking and air pollution associated with it. Is these researchers did a study on how polycyclic aromatic hydrocarbons such as benzene, toluene, and all those other lovely things that are in oil, diesel, and so on, what happens with fracking is it present within the air? So when they published the paper, they said, we reached the conclusion that fracking increases the concentrations of these harmful pHs in air. But then they look back at their data and they realize, oh my God, we made a horrible mistake, is they used the wrong ideal gas constant. As you know, there's different ones depending on the units. There's 8.314 and 0.08026, if I remember correctly. So they used one when they should have used the other, and they reached the opposite conclusion. When they crunched the numbers again with the correct ideal gas constant, they realized they got the totally opposite conclusion, and they found that they didn't find significant concentrations of pHs in the air as a result of fracking. And fracking is such a controversial subject that it's quite embarrassing to have to come out and say, we made a huge mistake, and sort of come out with your tail between your legs with something like that. So these are the consequences of not being on point with your lab math. Alternatively, if you're going into medicine, medical school, if your math is incorrect, you kill somebody, which is even worse than destroying an orbiter or reaching the wrong conclusion and embarrassing yourself in the literature. So some things to think about moving forward. So we'll start with dimensional analysis, which is the hallmark of lab math and the thing that everybody hates. But all it is just a fancy name for converting units, such as a liter is 1,000 milliliters, a nanogram is 1 times 10 to the minus 9 gram, and all those little tiny suffixes and prefixes. All it's doing is converting whatever number you're given with those units to the desired unit that you want to reach. And this PowerPoint will be provided to you that has a handy dandy table with all of the conversion factors. So these are all of the smaller ones from deci all the way down to pico, and there's different ways of expressing them. If you'll notice, you can say that 1 centimeter is 10 to the minus 2 meters, or you can say that 100 centimeters is 1 meter, and it's the same way, two sides of the same coin. It's the difference of saying, okay, 1 liter is 1,000 milliliters, or 1 milliliter is 0.0001 liters. It's the same thing, just a different way of expressing it. And on the other side is the very, very large units going into kilo, mega, giga, and all of these can be converted through the base unit, which are things like grams, meters, and so on. So on to the fun stuff. This is where a lot of students check out or have trouble with, is setting up these conversions. And if you can set them up, you're golden. On the top there is the correct way of doing it. Is you'll notice, and this is a terrible laser pointer, I'm sorry about that. You have milliliters on the top, and you divide by milliliters. So you know your conversion factor is 1 liter is 1,000 milliliters, but whether to put those milliliters on the top or the bottom, students have trouble with. And think of it this way, is you have your 30 milliliters being divided by 1. And so you want to cancel out those milliliters to get to liters. In order to do that, you have to divide milliliters by milliliters to get them to cancel out and equal to 1. So milliliters and milliliters cancel out when you divide them, and you get 1. What is an incorrect but common mistake is to put milliliters on top, but what you're essentially doing is you're multiplying those 2 milliliters. So instead of converting to liters, you're actually just having milliliters squared. So that's an incorrect way of doing the conversion. So I've put these in beautiful colors for your viewing pleasure, but you might also find that if you struggle with these kinds of calculations, to do it that way in your lab notebook or your labs or your assignments, is using the different colors to denote different units will make it easier to do these kinds of things and cancel them out. So do not do that. Do the one on the top. Here is a real-life example. All of these examples are things that have happened to me or that I have seen happen. So an annoyed doctor calls saying he wants the high-sensitivity C-reactive protein, which is a marker for inflammation that you get from a blood test. He does not want the regular CRP, and it gives you a value for a CRP. But, funny story, the high sensitivity and the regular CRP are the exact same thing. We get them off the same instrument, and it is just a matter of units. That's the only difference, is CRP is milligrams per deciliter, and the high sensitivity is milligrams per liter. So it's the same test, done the same way, on the same instrument, but with different units. Partially because the regular one versus the high sensitivity, they have different applications depending on what the numbers are. But this is a simple conversion. If we know that 1 liter is 10 deciliters, the only thing we need to do is convert from the 0.67 milligrams per deciliter to milligrams per liter. We're not changing anything with milligrams, so we go ahead and we set up our conversion factor. Is you start with what you know from the problem. So the problem gives us that 0.67 milligrams per deciliter. Then we plug in the conversion factor that we already know, set it up so that the deciliters and the deciliters cancel out, and you end up with your answer in milligrams per liter. And that's it. And if I'm talking too fast or I don't make any sense or you have any questions, by all means throw a hand up, yell, shout, whatever. So that's, in a nutshell, dimensional analysis. Another concept that is essential to understand is moles, which are not the cute, cuddly things pugging that test tube and inside that beaker. It is a unit of measurement designed by chemists to make your lives miserable. Not really, but it's used to standardize the amounts between different substances, because 1 mole of sugar is not going to be the same as a mole of benzene due to their different molecular weights. And chemical relationships are always done in terms of moles and never grams because of these different molecular weights. is we always work in moles. But they can be converted from grams, or molecules can be converted back to moles by these fundamental relationships. So 1 mole is equal to the molecular weight in grams, which you can get from the periodic table. So if we were looking at carbon, we'd say, okay, there's carbon, 12.01. That's 12.01 grams per 1 mole of carbon. And conversely, a mole is also 6.022 times 10 to the 23rd molecules, which you all have, ooh, I don't know how I did that, which you all have memorized by heart as Avogadro's number. Depending on your area of research, you may or may not be using that. So, as I said, 1 mole is 12.01 grams of carbon. This is another representation of that, a little map. Is no matter what we do, we always work from moles. So if I have something in a volume and I want to figure out molecules, I'll have to go through the conversion factor that's provided there between liters and moles, and then from moles to molecules. So you never go from grams of A to grams of B. You always go through moles, even though we don't want to. This is a graphic showing the difference of why we do this. In each of those beakers is 1 mole of each substance. So that's a mole of sucrose, a mole of copper, a mole of sodium chloride, and you notice that they're quite variable. There's a lot of the sucrose and not a lot of the copper, and that has to do with their different molecular weights. So keep that in mind when doing your calculations. They're not at all equivocal, so you must go through moles. So here's an example problem. How many moles are in 65.23 grams of sodium chloride? And look at that, there's a chunk of the periodic table right there with the elements that we need. How convenient. So we will be using that as our conversion factor, and 1 mole of sodium chloride is equal to that many grams. So when setting these up, always start with what you know. Take the information from the problem. So they gave us the 65.23. We use our conversion factor, cancel out grams and grams to get moles of sodium chloride, and that's it. We have our moles. Yet another concept that piggybacks off of moles is molarity, which is a unit of concentration that is used pretty universally in the sciences. And all it is the number of moles in the solution divided by the volume of the solution in liters. So a problem for that is to figure out how many grams we will need to make up the solution. That's 500 milliliters of a 3 molar solution. So keeping in mind how to calculate molarity, it's moles of solute per liters of solution. Well, we have the molarity. We know that we want it to be 3 molar, and we know we want the volume to be 500 milliliters. So we just need to solve to figure out how many moles we have, and then if we know how many moles we have, we can convert that to grams using the molecular weight. So one thing you want to do is make sure those milliliters are in liters, because you want to make sure you have the correct units. So divide by 1,000 milliliters, and you get your liters. And then plug that into the molarity equation. We know our molarity, we know our volume, so then we just multiply those two to get our number of moles. So we have our number of moles. But we have to refer back, what did the question ask us? And that's another problem, is you get so far into your calculations and you're going like, okay, I got it, I'm done. But then that's not what the question asked. So always refer back to what units were asked in the question, or what units you're trying to find. So we have the 1.5 moles, and we know that there's 40 grams per mole. So what we want to do is take that and convert it into grams using that conversion factor, and then we have our final answer. Dilutions, good times. So oftentimes we want to work with very, very small amounts of a substance, and in order to do that, we take a more concentrated solution and dilute it down to very tiny amounts to the point where there's barely anything in there. And this is the one take-home formula. If you ever remember any of them at all from chemistry, remember this one. C1V1 equals C2V2. Just think of the left and the right sides of the equation as one side is your concentrated solution that you're diluting from, and one is your final diluted solution that you're trying to make up, where your C's stand for the concentration of it and your V's stand for the volume of it. So typically how it works is you know 3 of the numbers, you just solve for the 4th. One example of this is commonly manufacturers will make a concentrated solution and send you a tiny bottle that's this big of whatever buffer or solution that you need, and then you have to make it up yourself. And you figure when you pay all that money, they might as well make up the solution for you, but that's not the case. So you have a 50x solution, and that just means it's 50 times concentrated, and they can use arbitrary units like that, which is great. And it comes in a teeny tiny 50 ml bottle, and you want to make a 1x buffer. So we have this information. We know that we have the original solution is 50x, and there's 50 mils of it, and we want to make a 1x buffer out of it. What's the final volume of that going to be? So then you just plug it in, solve for V2. So V2 ends up being, and your x's and x's cancel out so that your answer will be in milliliters. And that gives you a hint that you're on the right track to make sure that your units are canceling out. So the volume we get is 2,500 milliliters. But the question is, how much DI water are we going to add? And this is a common mistake. Oh, we add 2,500 milliliters to those 50 milliliters. That's not the case. The V2 is the final volume of that solution. So actually, what we're going to do is subtract from it the volume of the concentrated solution that we'll be adding in. So we have 50 milliliters of concentrated solution, 2,500 milliliters of the final solution. Simple subtraction, you get 2,450 milliliters of water that you're adding in. So that's yet another thing to pay close attention to. Parts per notation. Who's worked in parts per million, parts per billion, parts per trillion? A lot of molecular, biological, microbiological experiments use very small amounts, and parts per notation is very good to know. It's kind of difficult the first time you get acquainted with it because it doesn't have units like molarity does, which is moles per liter or grams per milliliter or something like that. It's dimensionless. There's no units associated with it, which is kind of strange. And it's used to express various small values, but if you think about it, a percent is also a dimensionless unit. A percent is not grams per liter, it's just a percent of what you have in the solution. So, for example, you have 1 part of your solute per 100 parts of solution with no other units associated with it. Parts per million, parts per billion, parts per trillion are basically the same thing. They grow off of that concept. So parts per million is just 1 part per 1 times 10 to the 6 parts, and parts per billion is 1 part per 1 times 10 to the 9 parts. And you're still thinking, how on earth do I calculate that 1 part why? There's other ways of expressing it. So one of the ways is milligrams per liter. And the reason, if you're like, why? Where did that come from? That seems so arbitrary. As it works out is a milligram is 1 times 10 to the third minus 3 grams, and 1 liter is 1 times 10 to the third milliliters, which are usually the standard units. And when they cancel out and give you that 1 times 10 to the 6. So that's the reason why it's used, is you have something really tiny like milligrams and something really large like liters, and it allows you to be able to express that in a way sort of like a percentage. That said, without knowing kind of the reference units that are typically used, it's hard to wrap your head around it. So this is typically how they're expressed, is these are all concentrations that are ways of saying parts per million or parts per billion. So a part per million, you can express it in milligrams per liter. So 1 part per million is 1 milligram per liter. Or it can be milligrams per kilogram, micrograms per milliliter, or 1,000 parts per billion, because it's 3 orders of magnitude larger than a part per billion. And conversely, there's different ways of expressing parts per billion, which is the same concept of the difference between the top unit and the bottom unit is 1 times 10 to the 9th. So that's where those come from. And if you need to just press the I believe button and just say, I don't get it, but as long as you know a part per million is a milligram per liter, that's all you need to know. That's it to get by. So, example of this is a real life example. I actually did this. So I study biodegradation of petroleum. So I made these incubations that were like mini Exxon Valdez's. So actual calculation, I performed real science. Yeah, get excited. So I wanted to use 50 parts per million of crude oil, and I had these 1 liter bottles, but I didn't want to fill them all the way up to the top. So I decided let's use 0.8 liters instead, so it's not going all the way up to the rim. And I know that, and this, I just noticed a mistake on this, the density of the oil, not the seawater, is 0.85 grams per milliliter, so make note of that. So we know what I want my concentration of oil to be, what the volume is going to be, and the density of it. How much am I supposed to pipette into this? Lots and lots of conversion factors. So we start with what I know. I want 50 parts per million. So a part per million is nothing more than milligrams per liter. So instead of saying 50 ppms, I said, okay, let's think of it as 50 milligrams per liter. But then I want to use 0.8 liters, not 1. So if I multiply that by the volume I want to use and cancel out my liters, okay, I didn't do that on the top one, then in the whole bottle in 0.8 liters, I will be using 40 milligrams of oil instead of 50 because I'm using less volume than 50 milligrams per liter. So with that 40 milligrams per liter, I want to use the density of oil to figure out how much am I pipetting in. So you can do, and there's many different ways to do this, is you can convert the milligrams to grams, or you can use that conversion factor of the density and change the grams to milligrams. There's more than one way to solve these things. This is just the way I approached it. So change the milligrams of oil that I want to get into grams, and then use that conversion factor that has the density of the oil. So grams and grams cancel out, and then I end up in milliliters, but it's going to be a really tiny amount, as I don't want to know how many 0.0000 milliliters I'm pipetting in. That doesn't mean anything to me, because I'm using one of these guys and putting in a really small amount, because 50 parts per million is not a lot. So I want to convert to microliters. Okay, 1,000 microliters in a milliliter, and milliliters cancel out, you get your answer in microliters. So I know in every single one of those 100-something bottles, I'm putting in 47.1 microliters of oil. Bam, real life example, right? Get excited. So in summary of all of the things I've talked about, at the end of the day, there's really not a lot of memorization you need to know with these things, as you can kind of keep a cheat sheet of the conversion factors in your lab notebook. We all do it. If I don't know it, I just Google it. What you need to know is how to approach them and how to set up the units to solve them. That's the only thing you really need to know. And if you have that problem solving there, everything else is secondary. So some things to keep in mind when approaching it is determine what's the problem asking for, or what problem are you trying to figure out. If it's for research, what's the exact answer with units that you're trying to address. Write down all the information that's given to you in the problem, or that you know, and start with what you do know to figure out what you don't. A lot of times it's, how am I supposed to figure out parts per million? Don't focus on that, because if I focused on everything I didn't know, I'd be having an existential crisis every day of my life. So take a look at what you do know and say, okay, I know I have this information. Where can I go from here? So use what you do know to figure out what you don't. Set up your conversion factors so that your units cancel out, so that you do not make horrible mistakes with your Mars orbiter or your fracking paper that you have to retract and embarrass yourself. Check that your answer matches what is being asked for, and just do these over and over and over again for the rest of your life until you're a pro. That's how you make perfect with them, and have someone check them if it's a really important one for paper. Email it to someone, send them your Google spreadsheet and say, hey, does this look right to you? because you don't want to be that guy that has your paper retracted.